Hello, Gen Chemers. What we're going to do today is talk about Module 3, which is about atomic theory, and then delving into the organization of the periodic table. So here we go. Let's start sharing the screen. Okay, so we're going to look at atomic theory. We're kind of going to go quickly through the development of atomic theory, and it sort of starts in ancient Greece, where we have Leucippus, who was active in 5th century BC, and then his student Democritus. And these were the first individuals to propose that matter was composed of small indestructible particles. Democritus wrote, "Nothing exists except atoms and empty space. Everything else is opinion." They proposed that many different kinds of atoms existed, each different in shape and size, and that they randomly moved through empty space. Now, this is actually pretty insightful considering they had no experimental knowledge, right? They had no technology in order to actually design experiments. This was all simply a thought process. Now, in that same time, Plato and Aristotle did not embrace the atomic ideas of Leucippus and Democritus. They held that matter had no smallest parts and that different substances were composed of various proportions of fire, air, earth, and water. Unfortunately, their ideas prevailed at the time. Again, there was no way to experimentally determine which group of scholars was correct. They actually were more popular in terms of impact in their society at the time. So Democritus's ideas actually sort of faded off until much later, and people could actually do experiments that allowed people to think about the nature of the atom. So it wasn't until the 1700s, the 1800s, that the scientific approach became the established way to learn about physical world. Now we had a way that we could actually devise experiments in order to test hypothesis. And it was English chemist John Dalton that offered very convincing evidence that supported the early atomic ideas of Leucippus and Democritus. The theory that all matter is composed of atoms and grew out of observations and laws. So we're going to look into 3 of the most important laws that led to the development and accepted of the atomic theory. This was the law of conservation of mass, the law of definite proportions, and the law of multiple proportions. These laws were the basis of what we now know as atomic theory. The law of conservation of mass is probably very similar to you. Mass is neither created nor destroyed in chemical reactions. If I look at this example, if I have an aqueous solution of mercury 2 nitrate and potassium iodide, and those will react. What I get is mercury 2 iodide, and I also get aqueous potassium nitrate. The idea here is what goes in comes out. Notice the amounts are not going to be the same because I've broken bonds and rearranged atoms. But the mass of the starting materials is equal to the mass of the products, because the number and type of atoms that go in are the number and types of atoms that come out, even though they've been rearranged into new substances. Here is what it might look like. I have Ki and I have mercury 2 nitrate. I'm going to go ahead and mix those together. I have a precipitate of the solid mercury 2 iodide. I can filter that. And then here I have my new substance, that mercury compound that actually precipitated out. And then this was still in solution. If I evaporated the water, I end up with potassium nitrate. And again, what I'm going to focus on is what comes in, comes out. The mass that went in is the mass that came out. The mass was neither created nor destroyed. I have the same number and types of atoms that go into the reaction as come out of the reaction. This law is consistent with the idea that matter is composed of small indestructible particles. Here's another example. If I have solid sodium reacting with gaseous chlorine, and if the mass that goes into this reaction is 19.6 grams, when they react together, I end up with the crystalline solid sodium chloride salt. And notice that the mass that comes out is going to be the same amount. So the mass of reactants is equal to the mass of the products because of the law of conservation of mass. The second law we're going to consider is the law of definite proportions. This law states that different samples of a pure chemical substance always contain the same proportion of elements by mass. If I look at water, any sample of water is always 88.8% oxygen and 11.2% hydrogen. All samples of any given compound, regardless of their source or how they were prepared, have the same proportions of their constituent elements. Water is always 88.8% oxygen and 11.2% hydrogen. If I don't have that ratio, if I don't have those definite proportions, I don't have water. This is sometimes stated as the law of constant composition. So sometimes you might look at it this way. If I decompose 18 grams of water, what I'll get is 16 grams of oxygen and 2 grams of hydrogen. And I can look at that oxygen to hydrogen mass ratio. I take the grams of oxygen to the grams of oxygen, or to the grams of hydrogen, and what I get is an 8-to-1 ratio between the oxygen and the hydrogen. The third law is the law of multiple proportion. Elements can combine in different ways to form different substances. The mass ratios are going to be small whole number multiples of each other. So I could have nitrogen monoxide, which is NO, or I can have nitrogen dioxide, which is NO2. In this case, I have a 1-to-1 ratio of nitrogen to oxygen atoms. I'll have 7 grams of nitrogen for every 8 grams of oxygen. If I have nitrogen dioxide, I'll have 7 grams of nitrogen for every 16 grams of oxygen. So I still have the two different elements that are combining to form these compounds. I have nitrogen and I have oxygen, but they combine in different ratios. But the mass ratios have to be small whole number ratios of each other. So when I get nitrogen monoxide, I have 1 nitrogen to 1 oxygen. When I get nitrogen dioxide, I have 1 nitrogen to 2 oxygen. Another way to state this is that elements can combine in different ways to form different substances, right? The mass ratios are always small whole number multiples. So again, when I look at NO, I have exactly 2 times as many oxygen atoms in NO2 as I have in NO, which is representative of this law of multiple proportions. Now, how did Dalton come up with his atomic theory based on these laws? Well, when you think about it, each element is composed of tiny, indestructible atoms or particles called atoms. So that's principle number 1. Any atom of a given element has the same mass and other properties that distinguish them from atoms of other elements. Atoms combine in simple whole number ratios to form compounds, and then atoms of one element cannot change into atoms of another element. In a chemical reaction, atoms only change the way that they are bound together with other atoms. So what I notice is that all of these basic principles sort of apply back to one of those laws that we just talked about. Moving on, it was later on that J.J. Thomson conducted cathode ray experiments. He constructed a partially evacuated glass tube called a cathode ray tube. He found that a beam of particles called cathode rays traveled from the negatively charged electrode, which was called the cathode, and the positively charged one, which was called the anode. So this is what it looked like. He's got the cathode, which is negatively charged, the anode, which is positively charged, and this stream of negatively charged particles flowed in this direction. So this stream is actually was a stream of electrons, and those cathode rays actually consist of those tiny negatively charged particles. So now we know that this was a stream of electrons that J.J. Thomson actually discovered. He also found that these electrons in this cathode ray stream have the following properties. So they travel in straight lines. They are independent of the composition of the material from which they originate. Electrons are electrons. It doesn't matter what they originate from. An electron is the same regardless of the source. And they carry a negative electrical charge. So these are the properties of electrons as we know them today. Thomson also measured the charge to mass ratio of electrons by deflecting them using electric and magnetic fields. If you look at this figure, he was able to shoot this beam of electrons, and by looking at the deflection, right, electric and magnetic fields are deflecting the electron beam, and he was able to discover what the charge was. He could calculate the charge in coulombs per gram of material, and that was minus 1.78 times 10 to the 3 coulombs. Now, the electron, as we know it, is a negatively charged low mass particle, right? So I have a negative charge, it's low mass, and it's present within all atoms. What do we know about charged particles? We know that opposite attracts. So I have positive and negative charges, they're going to attract one another. We know that like charges repel. Positive will repel other positives, negatives will repel other negatives. And we know that if I have a positive charge and a negative charge of exactly the same magnitude, they're going to equal to 0 when they're combined. So using these basic principles explains a lot about what we see in an atom. The next experiment we're going to look at was performed by Millikan, Robert Millikan is an American physicist, and he determined the mass and charge of an electron, a single electron, with his oil drop experiment. And this was done in 1909. So what he found was that the charge on an electron, a single electron, is negative 1.602 times 10 to the minus 19th coulombs. And he found that the mass of the electron was equal to 9.109 times 10 to the minus 28th grams. This is the experiment that he actually used to determine this. And let's look at this a little bit more closely. So here we have X-rays being beamed into this box. I have two electrically charged brass plates. Oil is sprayed into this pinhole, and they're going to progress down here where the oil individual charge droplet is sort of coming through here. What we know is as the oil droplets are allowed to reach their terminal velocity, you can calculate the mass of each individual drop. The falling drops are given a negative charge by X-rays and are suspended between the two electrical charges. By doing that, what I can look at is the charge on the drop can be calculated from the mass and the voltage on the plates. So if I look at this material and I look at what his results were, he measured, by measuring the strength of the electric field that was required to halt the free fall of those oil drops, and by figuring out the masses of the drops themselves. Now these are spherical drops so that the masses could be determined from their radii and their density. Millikan was able to calculate the charge of each drop. With this number in hand, and knowing Thomson's mass to charge ratio for electrons, we can deduce the mass of an electron. So if I look at charge times mass over charge, I can cancel out my charge, and what I'm going to get is the mass. Now I have another model to consider, which is Thomson's plum pudding model. J.J. Thomson proposed that the negatively charged electrons were small particles held within a positively charged sphere. So this is called the plum pudding model. So here I have this diffuse sphere of positive charge, and I have these electrons that are suspended in this fuse, in this system. And what I'm going to see is this was a proposal. This was Thomson's early idea of what an atom looked like. Now, around the same time, Henri Becquerel found that some materials produce invisible radiation, which consists of charged particles. This was called radioactivity, which is the spontaneous emission of very high energy radiation in particles. There are several different types of particles that can be emitted. I can have beta particles, which are basically high energy electrons, or I could have alpha particles, which is basically the nucleus of a helium atom, which has a +2 charge. In 1909, Rutherford actually had worked under Thomson and was a proponent. He subscribed to Thomson's plum pudding model. So he devised an experiment in order to confirm Thomson's plum pudding model. In this experiment, which is called the gold foil experiment, Rutherford directed positively charged alpha particles at an ultra-thin sheet of gold foil. So this is the experiment. I have this radioactive sample that's going to decay and emit this alpha particle. I have a very thin gold foil here. I have a zinc sulfide screen surrounding it. I have a lead block shield. And what I find is that some of the alpha particles actually are deflected and they hit back, and some are scattered, whereas others go straight through. So most alpha particles went straight through, but some of them were deflected. These deflections occurred at large angles, and a few actually bounced back towards the particle source. So what you can conclude for this is, because the majority of particles are not deflective, the gold atoms must be almost entirely empty space. The atom's mass is concentrated in a tiny, dense core, which deflects the occasional alpha particle attack. Now remember, these are positive. Like charges repel. So they think that the center of the nucleus was actually a positively charged nuclear idea here. So this brought forth the nuclear theory of the atom, which is that most of the atom's masses and all of its positive charge are contained in a small core called a nucleus. Remember, most of the atom's mass, all of its positive charge are in the nucleus. Most of the volume of the atom is empty space, and this is where my electrons are dispersed. There are as many negatively charged electrons outside the nucleus as there are inside the nucleus, and those were called protons, the positively charged protons, so that the atom is electrically neutral. So I just have now this sort of more familiar idea of the atom, where I have the center of the atom, which is the nucleus and contains protons, where the rest of the volume of the atom is containing the electrons. Now, Rutherford's model was highly successful, but it was incomplete. Later work by Rutherford, and actually one of his students, who is named James Chadwick, demonstrated that there was previously unaccounted for mass in the atom that could be due to neutrons, which are these neutral particles within the nucleus. So Chadwick bombarded a thin sheet of beryllium with alpha particles. Again, those are those positively charged particles. A very high energy radiation was emitted by the metal that was not deflected by either electric or magnetic fields. This radiation consisted of this third type of subatomic particles, which Chadwick named neutrons because they're electrically neutral. And they have a mass that's slightly greater than the proton. So all of the mass of the atom is going to reside in the nucleus and is going to consist of the protons and the neutrons. Remember, the electrons are negatively charged, they're outside the nucleus, and they really don't have much mass, so they're actually considered, they're not considered compared to the mass of the protons and the neutrons. Okay, we're going to stop here, and then we're going to continue by looking at atomic theory in a little bit more depth in a second lecture.